this video today, we're going to be looking at deriving what are known as the kinematic equations. So some equations that can help us relate these different concepts in this unit, such as displacement, acceleration, velocity, and all that algebraically, instead of you doing it graphically like we've been doing, because this can be sometimes a quicker way to predict the motion of an object without having to use the velocity graph. Now, that said, we'll be using the velocity graph to derive these equations because it's really just a shortcut for doing the same thing we've been doing already. So some key vocab, some key ways we've used this velocity graph in the past is we can obviously use it to find the velocity of an object at a certain point in time. We can do that just by looking at the graph. So at 0 seconds, this thing was at rest. At 3 seconds, it was going at 5 meters per second. Some other key ideas were displacement, or the change in position of an object. We can look at the area under the curve here. So this object, it's in the first quadrant here, it's moving in the positive direction. And so we see this area is above the 0 line, so it's displacing positively. That's just the area 1/2 the base, 3 seconds, times the height, 5 meters, 1/2, because we got a triangle. So this object has changed its position by 7.5 meters in the positive direction from wherever it was when it started. So if it started at, I don't know, -10 meters, it's now at -2.5 meters. It's become more positive by this value. The other idea here is acceleration. We've defined as the rate of change of velocity, so that's the slope of the line on this graph. And we can find that slope by doing rise over run. Since it's a linear graph here, we can just do rise divided by run. So 5 divided by 3, up 5 over 3. 1.6 repeating meters per second per second. Now, one thing to note about these equations we're about to find, they're only going to be valid with a constant acceleration. So only when the acceleration, the slope of the velocity versus time graph is the same can these equations be used. Now, that doesn't mean constant velocity. This velocity is changing, but the acceleration, the rate of change of the velocity over time, is the same for the whole interval. All right, so let's get to it. I'm going to start by just drawing a velocity versus time graph to work with. So we got time, we'll say in seconds, velocity in meters per second, and I'll just draw a line here. Now note, here I'm drawing a object starting with a positive velocity and accelerating positively, so it's getting faster. These equations that we find are going to work in any sort of situation. So if I have an object going like this, or an object going like that, as long as the acceleration is constant, so the constant slope, these equations will work out. And we'll show you at the end that that's the case. So let's label some variables on this graph. Let's start with the ending point and the starting point. So here I'm starting at some initial time, which I'll label as Ti for the initial time, ending at some final time, Tf for final. This object has some initial velocity, which I'll call Vi, and some final velocity, which we'll call Vf. Other information we could get from this graph is the slope would be the acceleration, right? The rise over the run. And that's actually going to be our first kinematic equation, just using that definition. So acceleration is the rate of change of velocity over time. So it's just the delta V over the delta T. And that's our first kinematic equation. Now, physicists don't always write it in this way. So delta V is really, two things. It's the change in velocity, so it's including both the Vf and the Vi. So it can be nice to separate that out. Delta meaning change in, meaning final minus initial. So Vf minus Vi. And we're going to be using delta a lot throughout the year, so it's important to start really remembering that it always means final minus initial. So that's another way to write this out. And you can also do some algebra A lot of times we use this equation to find a final velocity. So I can algebraically just move these things around. I can get VF equals VI plus A delta T. And you can, if you want on your own, take the time, try to do a little algebra, see how this equation is the same algebraically as this one. But either way, whether you use it in this form or this form, same equation. This is our first kinematic equation. It's relating the acceleration to the velocity and the time. This equation, if you look hard enough at it, can sort of look like our standard slope-intercept form for a linear equation, y equals mx plus b, where the y variable is our final velocity, so wherever we're at. Our b is our initial velocity, our starting point. A is our slope, and delta t is our x variable. So it's a good way to relate it to some math equations for lines you might be familiar with. All right, so that's involving a lot of our different variables here. So we've sort of used this definition, acceleration is the rate of change, to get that one. Now we can also think about displacement as the area under the curve. So the displacement, as this object goes along, starting at this time to this time, we could see as this area here. So this whole area here right under the curve. And we know how to find area one way, sort of using a little bit of a shortcut here, is the area of a parallelogram. So the area of a parallelogram, which is what we have here, right? We've got two different side lengths here and the same base. So we can use that to find this area. So area of a parallelogram, area is 1/2 base 1 plus base 2. Or actually, we could call this, instead of bases, we could do heights. h1 plus h2 times the base. So in the case of our variables here, we can say delta x, the area, is equal to 1/2. And then our two different heights are VF plus VI. You can also do VI plus VF, it doesn't matter. Math works out. And our base would be this delta t here. I guess when we did that first equation, we should have labeled, this is delta v, change in velocity. This is delta t, change in time. Okay. So that's another equation, another way to relate these variables. I'm just going to, a lot of times, this is just written as delta v over, not delta v vi plus vf over 2. So that's another way to relate position, time, and velocity. Now let's say this requires us to know these different things to find this delta x. What if we didn't know the final velocity? What if we instead knew the acceleration? Could we still find this delta x? And yes, we definitely could. So before we've thought about this sort of shape, instead of thinking of it as a parallelogram, we could think of it as a triangle and a rectangle. And we could find the area that way by adding the area of this triangle to the area of this rectangle. So let's do that. So delta x, the rectangle is easy, right? It's just delta t, and then my height here is just vi. Okay, so we got base delta t times height vi. And then we got to get this triangle on here. So triangle, 1/2 base times height, 1/2 my base delta t, and my height delta v. Now we just said we were trying to get an equation that didn't have VF. We wanted one without VF. We wanted it to maybe have A in case that's what we're given in a situation. So how can we get A in here? Well, we can go back to our first relationship. A is delta V over delta T. And I can rewrite that. So we have A is delta V over delta T. And I can rewrite that as delta V is A delta T. A little bit of algebra. And then I can just shove that in here instead of the delta V. So let's write this all out again. We got delta X equals Vi delta T. And just in physics, we usually write the delta T last. This is sort of like our X variable, right? When you're doing a quadratic, it's ax squared plus bx plus c. And in this case, delta T was on our x-axis. Plus 1/2. And instead of delta T, I'm going to have A. Now, A delta T times delta T is A delta T squared. So now I have an equation that relates the position, change in position, that is, sorry, the displacement, I should say, with the initial velocity of the time and the acceleration. So this might be more useful in a case where I know the acceleration, but I don't know the final velocity. Again, this is just an equation telling us what this area under the curve is. So we haven't really learned anything new here. We're just writing it out algebraically what we've done before. Same here. This is just, again, showing this area under the curve. This is just showing this rate of change, this slope here. There's one more equation, and this is for situations where I don't know the time. What if I don't know what these time values are? What if I don't know what delta T is and I still want to figure something out? So is there a way to get a way to relate these velocities and these accelerations and these displacements not involving time at all? Just like here we managed to get an equation that did not involve VF at all. Like how this equation does not involve delta X at all. And there is. We're again going to start with this one here. So let's write that out. And this is a really nice equation because these other ones you could have just drawn a velocity graph and found the area. When you don't know the times, that gets a lot more difficult. So using this algebraic way can be very helpful. So we got delta X equals our velocities, VF plus VI. Again, usually you'll see this run written as VI plus VF, but same thing, delta T. And I want to get rid of delta T. So I'm going to look and I say, okay, what could I substitute out for delta T? Well, I could do sort of like what I did here, where I got rid of delta V, except this time I could get rid of the delta T instead. So if A equals delta V over delta T, I could rewrite this, and again, you could take some time, pause the video, maybe figure out the algebra for yourself. But here I'm just moving the delta V over here and the A on the bottom. And now I can substitute that in here for this delta T. And when I do that, delta X equals VF plus VI times delta V, and delta V, remember, is just VF minus VI over 2 times A. Okay, now this looks kind of messy. All right, we got VF plus, VF minus, but if we remember our mathematics, we know that A plus B times A minus B is A squared minus B squared. That's a mathematic identity you're hopefully familiar with or have seen sometime in the past. So we can rewrite this as VF squared minus VI squared over 2A. And again, that's equal to, following it back, that's equal to delta x. A lot of the time, this is not written this way. We don't like having things in the denominator. So we'll move the 2A over to the other side. So a little bit more room there. That way we don't have to have this division going on here. And then that will be our fourth kinematic equation. Those are our four kinematic equations, nothing new, just a different way to find area under the curve algebraically and the slope. All right, so those are them. You can stop now if you want, but if you want to be like, well, how do I know this works in other situations where I don't have a positive velocity and a positive acceleration? And you could just draw out those different situations and do the algebra just like we did before to see that you get the same things, but I'll just show you one example real quick. Let's say I've got this going on. So this is a little bit more complicated, right? I have an initial positive velocity, so I'm moving in the positive direction, but I have a negative acceleration. That negative acceleration is causing me to slow down, become less positive, eventually stop for an instant in time, and then speed up in the other direction, becoming negative, going the other way as I cross the axis here, right? So here I'm moving one direction. I'm slowing down, but I'm still moving positively. Here I'm moving negatively and speeding up. And do these equations still hold true? It turns out, yes, they do, because we did everything completely algebraically. Some signs and things like that are going to change, but it's still going to work out to get what we want. And I'm just going to show you with one example. I guess real quick, you can definitely see that our first equation, A is delta V over delta T, still works. That still finds us the slope, but let's look at something a little bit more complicated, like this one. The delta x equals VI delta T. Gotta match my colors. Plus 1/2 A delta T squared. One thing to note is that here the acceleration is going to be a negative value. So while these say they're adding, in reality when we plug in the negative for the acceleration here, we're going to get this value minus this value. All right, and this is represented graphically by this area minus this area, because this is on the negative portion of the graph, is below the x-axis. All right, so let's again think about what do these things represent graphically? Well, VI delta T, what does that look like on the graph? Well, that's this VI here. So it's this height times this base. So that's going to give us the area of this rectangle, basically, because vi is the height, delta t is the base. So that definitely doesn't look like this area, but let's see what happens when we add this other bit. This 1/2 a delta t squared, if you remember how we got it, a I can always just write as delta v over delta t. All right, rise over run. So I could write this as 1/2 delta v over delta t. That's what a is. I'm plugging in for a, times delta t squared. And here I've got a delta t and a delta t, so I can cancel off the square and I can cancel off the delta t in the bottom. And now this is the formula for the area of a triangle, 1/2 base times height. So that would be this triangle here. All right. I've got, let's pick a color for that, light green. So you can see, my base is delta t of this triangle, and my height is delta v. In this case, it's going to be, I chose this part and I didn't do this one because we're going to get a negative delta v here. All right, so this will be subtracting this value because we have this negative delta v. So we're looking at the orange area minus the light green area here. And we'll see, well, this bit in the middle, they cancel each other out here. All right, it's the orange minus the green in here, so I just get nothing. And I'm left with this orange piece minus this green piece, which you'll see lines up exactly with the areas that we want, the blue and the blue. So this equation still works given negative accelerations or negative velocities and all that, as long as you remember to include those negatives when you plug in to your variables. These equations will still get you the correct area for the displacement.